Alright, welcome to 2-1, the derivative and the tangent line problem. So to frame this tangent line problem, let's just start with this function that you see graphed in black, and this is our function f of x. And then we've got this red line going through two separate points on that function. This is referred to as a secant line. So when you hear me refer to a secant line, I'm just talking about a line that's crossing through a function's graph at 2 points that are kind of near each other, not super close, but relatively near each other. All right, and so the question that I have for you is, how would we find the slope of that secant line? Well, if you recall way back from Math 1, or even prior to that if you recall, to find the slope, you're just doing the slope formula, y2 minus y1 over x2 minus x1. And remember, that's when you have the two different points, x1, y1, and x2, y2. Another way that you could actually express the same slope formula is using delta y over delta x. And I just wanted to at least make sure you've seen that notation. In math and science, delta, the Greek letter delta, it just means change. Okay, so it's the change in the y values, and it's the change in the x values. Okay, so now going over back here to the graph, let's label this first point just as x comma f of x. I know that we can actually see that the coordinates there are 0, 1, but I'm less concerned about the precise coordinates and just about representing its location. So we're going to call that first one x comma f of x. So again, notice that down here, this is just whatever x is. Now for the second point, the x coordinate is over here, and I want to call the distance between these x's h. So again, h is measuring the distance between x and the second x coordinate. Well, if that's the case, if this first x coordinate is x and this distance is h, then it follows that the x coordinate for the second point must be x plus h. And that means that we can now rewrite the coordinates of the second point as x plus h, comma, f of x plus h. So these are the two coordinates that we're going to use for the slope. So now if I come back here to the slope formula, then that means it's y2, so f of x plus h, minus y1, which is f of x, over x sub 2, which is x plus h, minus our x1, which is just x. Now notice in the denominator, the x's do cancel out. So I can finally simplify this expression to f of x plus h minus f of x all over h. So this expression here represents the slope of the secant line. And I'm hoping that you recognize this as the difference quotient, which you learned in pre-calculus. So the difference quotient really is just a fancy way of writing the slope of a secant line. Okay, so again, that's the slope of the secant line. So now here's the challenge. If a secant line goes through 2 points, we have also something called the tangent line. And the tangent line would intersect the graph at exactly 1 point in a relative nearby location. So in other words, the tangent line at this point here, x comma f of x, might look something like this. That was not the greatest line. There we go. So the tangent line would look something like that. It's crossing the line at exactly 1 point. It doesn't hit the graph again, at least not relatively nearby. Well, how would I find the slope of the tangent line? That's the question. How do I find the slope of the tangent line? Well, I can't use the slope formula because the slope formula relies on having 2 separate points. And if it's a tangent line, I only have 1 point on the line. So let's think about it this way. for the secant line, what if I drag the second point closer to the first point? So maybe right there. Well, now I could still find the slope of that secant line, and that secant line does start to get closer and closer to becoming the tangent line. So our game plan then to find the slope of that tangent line is we want to find the slope of the secant line where the second point is as close as possible to the first point. But now, remember how we defined the second point. Remember that the second point was defined where the x-coordinate was x plus h. So if I'm trying to bring the second point closer and closer to the first point, think about what's happening to the value of h. So as the second point moves closer and closer to the first point, h seems to be getting smaller and smaller. Or in maybe words that are more familiar to us, h is approaching 0. So what that means then is to find the slope of the tangent line, we can take the limit of our difference quotient, which remember is the slope of the secant line. So we're doing this, the limit of the slope of the secant line as h gets closer and closer to 0. In other words, as the second point gets closer and closer to the first point. And this right here would give us the slope of the tangent line. In calculus, the slope of the tangent line is better known as the derivative. So we are now looking at this thing called the derivative, which represents the slope of the tangent line to a function. So here's our definition then for the derivative. So the derivative of a function f at x is given by this notation here. So this is read as f prime of x. Again, this is read as f prime of x is the limit of the difference quotient as h approaches 0. You do need to make sure you've memorized this limit here. Okay, so the derivative, which gives us the slope of the tangent line, is f prime of x equals the limit of the difference quotient as h approaches 0, provided that the limit exists. And notice this is f prime of x. That means f prime is actually a function in terms of x. So remember, the slope is just a number, but this is telling us the slope of the tangent line at any particular value of x. And that's why the derivative is a function of x. What the derivative gives us is a formula that will then allow us to find the specific numeric slope at any particular value of x. When we use this limit definition, that's referred to in directions as the limit definition, or sometimes they'll refer to it as the limit process. So if a question ever asks you to find the derivative using the limit definition or find the derivative using the limit process, again the key word here being the limit, then what they are asking you to do is to use this formal definition here. Okay. Okay, so let's look at an example here. So example 1. For the function f of x equals x squared minus 2x. First, we're going to find the derivative of f using the limit process. Okay, so remember, that means we are using f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. So now what we need to do is we need to be able to substitute. We need to find the expression for f of x plus h. We already know f of x. F of x was given to us. That's x squared minus 2x. But we need to get an expression for f of x plus h. Now remember, what that means is in the original function, everywhere I have an x, I'm replacing it with x plus h. So f of x plus h, I'm going to kind of do this work off on the side. So in fact, let me move this to the side. So f of x plus h means in f of x, where we would normally have an x being squared and then a 2 times an x, I'm going to replace those with my x plus h. Okay, so that means this limit now becomes the limit as h approaches 0 of x plus h squared minus 2 times x plus h. So again, all of that was just our f of x plus h minus f of x, which remember is x squared minus 2x, all over h. All right, so now we've got some simplifying to do. Now up in the numerator, we are squaring x plus h, so we actually need to expand that. So if I square x plus h, that's going to give me x squared plus 2xh plus h squared minus 2x minus 2h when I distribute that negative 2. And then minus the x squared minus 2x that we have at the end, all over h. So again, all of this is f of x plus h. All of this is f of x plus h as we start to expand it. This right here was our f of x. Okay, so now let's go ahead and distribute this subtraction right here so that we can start simplifying the numerator a little bit. So now I have the limit as h approaches 0. So in the numerator, I'm going to go ahead and just do x squared plus 2xh plus h squared minus 2x minus 2h. And then now when I distribute the negative, I have minus x squared plus 2x. Be very careful of your signs here. All over h. So now let's look for some like terms that we can simplify here. So let's see. I notice right here that I have a minus 2x and a plus 2x, so those are going to go away. I have an x squared and a minus x squared, so those are going to go away. And I have no other like terms, so let's go ahead and clean this up a little bit. I have the limit as h approaches 0 of 2xh plus h squared minus 2h all over h. If I were to use direct substitution right now, now notice we're dealing with h approaching 0. So if I were to use direct substitution, remember that we would be substituting for h, not for x. And if I were to do that, I would get 0 over 0. So I do need to continue rewriting this function. Well, I can definitely factor out an h from the numerator. And that means I'm going to have 2x plus h minus 2 all over h. That h and that h now cancel out. And now I have the limit as h approaches 0 of 2x plus h minus 2. So now let's do our final substitution here. Again, remember, because this is h approaching 0, we are only substituting for h. Any other variables that you see are actually considered sort of almost like a constant. We leave it alone. So the limit of 2x as h approaches 0 is still 2x. The limit of h as h approaches 0 becomes 0 though, because that one we are substituting. And then the limit of negative 2 as h approaches 0 is still minus 2. And finally we get 2x minus 2. And that right there is the derivative of x squared minus 2x. This is the function that we would be able to use to find the slope at any value of x. Okay, so part B of the same question. What is the slope of the tangent line to f of x at x equals 3? Well, remember, if they're asking for the slope of the tangent line to f of x at x equals 3, the slope of the tangent line means f prime, and because they're specifically asking at x equals 3, they're really asking for f prime of 3. So that's what this question is asking. But remember, in the previous question, we found that f prime of x was 2x minus 2. This is the derivative that we just found in part A. So for part B, to find f prime of 3, we're just going to substitute into our derivative. So that means I'm going to have 2 times 3 minus 2, which is going to be 6 minus 2, which gives us 4. So that means the slope of the tangent to the original function f at x equals 3 is 4. So the slope of that tangent line would be 4. And then finally for this question, part C, write an equation of the tangent line to f of x at x equals 3. In this course, when you see write an equation of the tangent line, there are two things that you need to know. You need to know the slope of the tangent line, and you need to know the point where the tangent line intersects the graph. Now, the slope of the tangent line, as you've heard me say multiple times, that is the derivative. So if they're asking for the equation of the tangent line, then that means the slope is the same as f prime, in this case, of 3. But we just found in part B that that slope is 4. To find the equation of a line, though, in addition to the slope, we need to know a point on the line. Specifically, we need to know the point where our tangent line intersects the graph. So that means our point has to be 3, comma, f of 3. So we need to figure out what is f of 3. Now remember, the original function was x squared minus 2x. So f of 3 is going to be 3 squared minus 2 times 3. That's going to be 9 minus 6, or just 3. So that means our point is really 3, comma 3. So finally, to write the equation of a tangent line, you learned how to write the equation of a line way back in Math 1, and we can use point-slope form. This formula you should actually already have memorized from previous courses. So if you don't have that formula memorized, start working on that now. So remember, to use this formula, m is your slope, which we found, and x1, y1 are the coordinates of a point on the line, which in this case is the point of tangent C, the point where the tangent line hits the graph. So I can now substitute. I have y minus 3 equals our slope, which is 4, times x minus our x1, which is also 3. And this is our equation of our tangent line. We do not need to put this in slope-intercept form, so this is actually our answer right here. And just to illustrate what it is that we found, so here is our function, f of x equals x squared minus 2x. Here's the point of tangency that we're talking about, 3, comma 3. And right here, here's the equation that we just found for the tangent line, and if I activate that, you can now see that we've got this tangent line. So again, here's our function, and here's our tangent line. Okay, so now that you've seen that whole process, sort of stretched out, lengthy time-wise, so let's now do another example just so you can sort of see the process a little less interrupted. All right, so we're going to start by finding f prime of x using the limit process, and this time our function is f of x equals the square root of x plus 3. So remember, if I'm looking for f prime of x using the limit process, then I'm looking at the limit as h approaches 0 of f of x plus h minus f of x all over h. But that means f of x plus h is really the square root of x plus h plus 3. So let's go ahead and substitute that now. So now we've got the limit as h approaches 0 of the square root of x plus h plus 3, so that's my f of x plus h, minus f of x, which is just square root of x plus 3, all over h. All right, if I wanted to evaluate this limit, if I were to use direct substitution for h, I would get 0 over 0, which is going to be indeterminate. So I do need to try something else. Well, I have radicals, so I'm going to multiply by the conjugate. When I multiply by the conjugate, then that means the numerator now becomes x plus h plus 3. Notice I'm using the parentheses. I definitely recommend that you use parentheses here just so you don't make a sign error on this next part. Minus square root of x plus 3 squared becomes x plus 3, but remember you're subtracting that whole quantity, all over h times, and here's a common mistake, don't forget that the denominator also got multiplied. So don't leave off this factor in the denominator. All right, so now in the numerator, notice that the x's, I'm going to have an x minus an x, so those are going to cancel out. I'm going to have a 3 minus a 3, so those are also going to cancel out. So all I'm left with then right now in the numerator is that h. And then now, as you can hopefully see, those h's also divide out, leaving me with a 1 in the numerator. And so finally, we have this. Ooh, I don't know if anyone caught it. I assumed that I had done the conjugate. This should have been a plus. Hopefully you all caught that. So this is a plus, this is a plus, this is still a minus, but this is a plus, this is a plus, and this is a plus. Sorry about that. You probably already noticed that. Okay, so now finally, to evaluate this limit, I can replace the h with a 0. So I get 1 over the square root of x plus 3 plus another square root of x plus 3. And that finally just becomes 1 over 2 times the square root of x plus 3. And that is our derivative. All right, part B of the same question. Write an equation of the tangent line to f of x at x equals 6. So again, there are those key words. Write an equation of the tangent line. So again, in order to do that, I need to know the slope, which is, if it's the slope of the tangent line, then that's going to be f prime, in this case, at 6. Well, we just saw in the previous problem, I'll write it over here on the side for reference. Remember, we just found that f prime of x is 1 over 2 times the square root of x plus 3. So f prime of 6 is going to be 1 over 2 times the square root of 6 plus 3. Well, 6 plus 3 is 9, square root of 9 is 3, 2 times 3 is 6, so I just get 1/6 as my slope. Remember, we also need to know the coordinates at that point of tangency. So that's going to be 6, comma, f of 6, not f prime, f. So that means we have to substitute into the original function. Remember that the original function was just the square root of x plus 3. So f of 6 is going to be the square root of 6 plus 3, which is going to give us square root of 9, or 3. So that means our point is 6, comma 3. So finally, we can now substitute into our point slope formula. Remember, we're going to replace the m, the slope, with our derivative, and we're going to replace the x1 and the y1 with the coordinates from our point of tangency. So finally, this becomes y minus 3 equals 1/6 times x minus 6. And that's the equation of our tangent line. Okay, now, what you've been finding so far is the derivative of the function. And again, what that gave us, as you can see up here, what that gave us was actually a formula that we were able to use to find the slope of a tangent line at any value of x. So the benefit of finding this function f prime of x is that that now allows us to find the slope at various values of x. But what if I only need to know the slope of the tangent at one specific x value and I don't care about any other place? There is an alternate form of the derivative that we can use in that situation when we're only trying to find the slope of the tangent at one specific point. So this is the alternate form of the derivative. And again, we would use this if we are specifically just trying to find the slope of the tangent at one specific value. So to find the slope of the tangent line to f at the point x equals c, we would use f prime of c, and again, this is the slope. So we would use m equals f prime of c, which equals the limit as x approaches c. So notice right away, here's a big difference. From the limit definition, that was the limit as h approaches 0. For this alternate form, we're doing the limit as x approaches c. So that's the first difference. Here's the big second difference. This is of f of x minus f of c over x minus c. Now remember, f of x is just the original function. F of c is the y value of the function when x is c. So f of c is a number. C is also a number. So that's the alternate form of the derivative. So let's go ahead and use that. Okay, so use the alternate form of the derivative to find the slope of the tangent line to f of x equals x cubed minus 7 at x equals 2. So this is my f of x right here at x equals 2. So in other words, 2 is my c value. Okay, so if I'm finding the slope of the tangent line, that's our m, better known as f prime. And I'm trying to find f prime of 2. So if I'm using the alternate form, then that means I want the limit as x approaches 2. Now remember, this is going to be of f of x minus f of c. So it's f of x minus f of c over x minus c. But remember, in this particular example, 2 is our c. So everywhere I'm putting a c, that's now going to be a 2. All right, so now let's go ahead and start substituting some things here. So f of x, remember, is x cubed minus 7. Minus, now f of 2, let's go ahead and work that out on the side. F of 2 is going to be 2 cubed minus 7. 2 cubed is 8. 8 minus 7 is 1. So this is now going to be minus 1 over x minus 2. Now in the numerator, I have x cubed minus 7 minus 1, so that's going to be x cubed minus 8 over x minus 2. And now this limit looks exactly like what you've been doing in the last unit. So first, if I use direct substitution, I am going to get 0 over 0, so I do need to try something else. Let's go ahead and factor this. The numerator is a difference of 2 cubes. That's going to be x minus 2 times x squared plus 2x plus 4 all over x minus 2. Those x minus 2's cancel out, and I just get the limit as x approaches 2 of x squared plus 2x plus 4. And when I substitute, that's going to give me 12. So that's the alternate form of the derivative. Okay, up to this point, when we've referred to the derivative, you've seen me use the notation f prime of x. And that's going to be one of the most common ways that you're going to see the derivative notated. So this is when you've got a function f of x, so its derivative would be f prime of x. If the function were called g of x, then you would write g prime of x for its derivative, okay? However, there are other notations that are going to be commonly used throughout this course, so I wanted to make sure that we were aware of them up front. Some of them we are going to use in more particular situations than others. So again, if the function is called f, then we would use f prime. So sometimes, though, especially within maybe a theorem or a definition, sometimes it will refer to the derivative simply as f prime instead of f prime of x, so just be aware of that. But remember, lots of our functions we don't even call f of x or g of x. A lot of them just start with a y equals. And if the function starts with a y equals, then the derivative would be notated for those as y prime. Now, there's another notation that we're going to use quite a bit in certain circumstances, and it looks like this. We have a dy over dx. And the way that you read this one, it's the derivative of y with respect to x. And what that means is we're dealing with the function that was called y equals, and the independent variable of that function was x. That's what that notation is just trying to say. So if I had a function instead that maybe instead of y equals and it being in terms of x, maybe the function was h equals and maybe it's in terms of t. And if that was the case, then this same notation would be written dh dt. We're saying we want the derivative of this function h in terms of the independent variable t. So that's what that notation is trying to say. But again, that's only if the function is called y equals or h equals. What if the function is still called f of x? Well, alternatively, we can write it as this. The derivative of f of x with respect to x. Now, the reason it's sort of bumped out here to the right side is this just looks a little bit too clunky because you're trying to fit too much there up in the numerator. So that's why they've kind of moved the f of x out to the side. But it's based on the same idea as dy dx. And then finally, oftentimes you'll see us just use brackets around the function itself and then putting a prime on the outside. So these are all different notations that you might see referring to the derivative of a function. Okay, and we're going to wrap up this lesson by just talking about this idea of a derivative existing or not existing. Since a derivative is a limit, and as you saw in the previous unit, not all limits exist, so it must follow then that since a derivative is a limit, it does not always exist. The derivative doesn't necessarily have to exist. So when the derivative does not exist at x equals c, we say that f is not differentiable at x equals c. So the word differentiable means that the derivative exists. So if the derivative does not exist, we say that f is not differentiable at x equals c. Now this could happen in a few different ways. So one of the ways that a function might not be differentiable at x equals c is if you have a non-removable discontinuity at x equals c. So if you have a non-removable discontinuity at x equals c, then the derivative does not exist. And what that means then is, and I do want you to remember this phrase, differentiability implies continuity. And what that's saying is, if you know that the derivative exists at a point, then it's guaranteed that the function must be continuous at that point. Now, that's going to be important for us moving forward because remember, many of the theorems that we work with in this class will require that we know that a function is continuous. And if we know that a function is differentiable, then it's like a 2-for-1. We know that if the function is differentiable at the point, then we already know that the function is also continuous there. Okay? But if we have a non-removable discontinuity at a point, then we definitely know that the derivative does not exist there. A second way that a derivative might not exist, that a function is not differentiable, is if you have a vertical tangent line. So the most common example of this is dealing with the function cubed root of x. So hopefully, as you recall from your previous courses, the graph of the cubed root of x looks like this. And I want us to investigate this point right here at 0, 0. If I were drawing my tangent lines to this function, notice that when I get to 0, 0, the tangent line turns out to be vertical. Now remember that the derivative represents the slope of the tangent line. But if my tangent line is vertical, hopefully you recall from previous courses that a vertical line has no slope, or in other words, the slope is undefined. And if it's undefined, then that means it doesn't exist. But the slope of the tangent line is the derivative. So that's why if you have a vertical tangent line for a function, then that means this function is not differentiable at x equals 0 in this particular case. And the third and final way that a function might be not differentiable at a point is if you have a corner point or a cusp. These are both basically the same idea. You have a sharp point. The difference being a corner point is caused by two straight lines, maybe kind of like the vertex of an absolute value function, versus a cusp, which might be something like this, where it's a sharp point, but it's formed by two curves. Okay, but again, the main idea here is both of those are giving you a sharp point. And a function that has a sharp point is not differentiable at that point. Now, the reason for that, we have this idea of something called local linearity. We've been talking about these tangent lines to a function, but another way to think about what a tangent line is that if you were to zoom into a graph super close, if you were to zoom into this point, eventually you wouldn't be able to tell the difference between the tangent line at that point and the curve itself. Let me show you what I mean real quick. So let's go back to that tangent line and graph that we looked at way back in example 1. So right here we have our tangent line at 3, 3. Let's zoom in close to that point. So you can still see the difference between the curved graph and the tangent line. But again, I'm going to continue zooming in closer and closer and closer. And eventually, the two graphs seem to overlap. So this idea of local linearity is, if you can zoom into a graph close enough where eventually the curve looks like a line, then you've got a tangent line there. But think about then absolute value. So here's the absolute value of x, and I'm interested in the vertex right here at 0, 0. Watch what happens when we zoom in. So you saw previously when I zoomed in enough, eventually the curve and the tangent line became the same. But I'm still just zooming in, and that corner point is not giving up. So that's this idea behind local linearity. If you have a part of a graph or a point on a graph where no matter how far you zoom in, it never starts to look like its tangent line, then the function is not differentiable at that point. So to wrap up here, let's describe the x values at which f is differentiable. So to answer a question like this, we're actually going to first start by thinking of the opposite. At what values of x is this function not differentiable? So that's the first thing we're going to think of. So at what values of x is this function not differentiable? We just went through a list of 3 different ways that that could happen. Well, clearly on this graph, we've got a discontinuity at -2. So we know that this function is not differentiable. So we know this function is not differentiable at x equals -2 because we have a discontinuity there. Same story here at +2. We've got another discontinuity there. So we also know that f is not differentiable at x equals +2. Okay, we don't have any other discontinuities. We don't have any corner points or cusps, and we don't have any vertical tangent lines. So these are the only 2 places where f is not differentiable. So to answer the question, describe the x values at which f is differentiable, we're just going to describe the intervals now for everything else. So remember, what we're really saying is on a number line, we want everything except -2 or 2. So that means we have 3 different intervals we need to describe. So that means f is differentiable from -infinity to -2, not including -2, from -2 to 2, and finally from 2 to infinity. Okay, so that was quite a lot to take in, but at this point, the things you should be able to do. You should be able to find the derivative of a function using the limit process. You should be able to write the equation of a tangent line using that derivative. You should be able to use the alternate form of the derivative to also find the slope of the tangent line. You should now be familiar with different notations that indicate the derivative. And you should be able to describe values of x at which a function is differentiable for a given graph.